So continuing with Voronoi diagrams from last time, um, we said that Voronoi diagrams store proximity information, and for every point in the plane, every point of the point set that you're given, it constructs the locus of points, the convex polygon, whose interior points are closer to that point than to any other point. Okay, and we mentioned that it captures a lot of problems where proximity information is important, and it covers a lot of ground. It works in different metrics, not just Euclidean. There's dynamic versions, and the dynamic versions allow points to move and still keep the Voronoi diagram maintained properly as points move, or even when points are inserted or deleted, as well as moving around. There's entire conferences on this subject, and a lot of art and architecture incorporates Voronoi diagram kind of motifs in it. It's very ubiquitous. Even nature has Voronoi diagram kind of structures, and for good reasons. You can read more about it, for extra credit, why that happens. We mentioned a term project idea for Voronoi art to maybe augment your TSP kind of art that maybe you're already working on, or just an alternate project. There's the Voronoi Mona Lisa, Voronoi cat, pretty cute. We said that the unbounded cells of a Voronoi diagram are associated with convex Hall points, so that gives you a nice association of convex Hall points and the Voronoi cells, which are the unbounded ones. So for free, essentially, you get the convex Hall. Nearest neighbors are across Voronoi diagram neighboring regions, and so that's an easy way of finding all nearest neighbors very quickly. It's a planar subdivision, so you can search a Voronoi diagram for point location, arbitrary point queries in logarithmic time based on planar subdivision search, which is the technique we showed a couple of weeks ago. And the dual, the graph dual of the Voronoi diagram is a Delaunay triangulation. That's better. So the Delaunay triangulation, basically you connect all points which have a neighboring Voronoi diagram cell border, a joint border, and it gives you a nice triangulation. It has a property that it minimizes, it maximizes the minimum angle over all possible triangulations. It could be an exponential number of those. And minimum spanning trees are a subset of the proximity diagram of the Delaunay triangulation, actually. And so we said there's a lot of problems, all of which require n log n lower bound, and they're all doable in n log n upper bound once you have the Voronoi diagram. So then the question is, how do you solve all these problems in optimal time? And the short answer is by obtaining the Voronoi diagram first. And so the question now reduces to how do you get the Voronoi diagram, and how do you do it quickly? So we'll start with a kind of a simpler algorithm first. So to get the Voronoi diagram, you can use the fact that a Voronoi cell is the intersection of all the half planes, which are the perpendicular bisectors of pairs of points, one of them being the target point. Okay? And before we even do that, let's give a even simpler algorithm where the points are in a bitmap. So you have a big bitmap, and m by n, or say n by n large bitmap, say 1,000,000 by 1,000,000 pixels, or any number of pixels. And you want to find all the points that are closer to a given point than to any other point. So what you can do is expand wavefronts from all the points. Again, this is assuming it's a bitmap, which often it isn't, but we'll look at the other case, the more general case in a minute. So starting at all the bits, which are the points that are given to you in the bitmap, start marking all the points by an expanding wavefront from each point. And when wavefronts meet, freeze the points there and stop the expansion process when two different wavefronts meet and crash into each other. Then freeze the expansion right there, but keep expanding everywhere else. And soon enough, you'll have the Voronoi regions kind of marked out in the bitmap. You keep marking the bits with the indices of the points where the wavefront started. It's possibly easier to see this in a color-coded way. So in a color-coded way, all the points with an expanding wave are marked with that particular color of the point that's where the wave started expanding from. And you get the Voronoi diagram pretty quickly. So this works nicely for bitmaps. How many get this approach? It's pretty straightforward. Just expanding wave fronts, and then when they collide, they freeze. Now, the issue is that the total time is the size of the bitmap itself. So if you have a million by million bitmap, which is a very large bitmap, the time will be 1,000,000 squared roughly. I mean, just to initialize all the storage will take you that long. So it's roughly the size linear in the bitmap. On the bright side, it's independent of the number of points. So it doesn't matter how many points you have marked originally in the bitmap, the time will still be proportional to the size of the bitmap, independent of the number of points of the bitmap. So, and the other issue is it identifies the pixels, not actual polygons. So this identifies which pixels are in each region, not the actual polygons. So it's a bit, of a special case, this kind of approach. Now let's look at a more general case. So we notice that the Voronoi cell of a point is the intersection of all the half-planes associated with that point. And here's what we mean by half-plane. Draw a line to some particular neighboring point like this, and look at the perpendicular bisector. So all the points on the left of this red line are closer to this red point than all the points on the right of this red line, which are closer to the blue point, not the red point. How many can see that? Just perpendicular bisector, pretty straightforward relationship. So the Voronoi cell is on the left of this line, not any of it is on the right of that line. The Voronoi cell of this red point here. And you do the same thing for other points. So similarly, by the same reasoning, the Voronoi cell associated with this point is on the lower portion of the half plane of this red line, not on the upper portion of the half plane. So as you keep drawing these half planes, those demarcate the boundaries of the Voronoi cell, one boundary at a time. So for this point, you draw this half plane, and the Voronoi cell is basically the intersection of all these half planes, the proper side of all these half planes. And I marked this graphic with this kind of fuzzy area on one side of the line is the correct half plane. The other side is the other half plane that we're not concerned with, that we're not interested in. So the Voronoi cell is simply the intersection of all these half planes, of the perpendicular bisectors between that point and all the other points. And once you keep doing that, very quickly you get the Voronoi cell of that red point. So one more plane intersected, one more half plane intersected with all the previous half planes, and voila, you get this Voronoi region right here in red, in solid bold red, and that's the Voronoi cell of that point. Now, why didn't I access or do the same in parallel perpendicular bisector kind of issue with the other points? Well, I did. You do all of them, but I just showed you kind of the relevant ones. Once you do perpendicular bisectors with some of these other ones, like for example this one, the Voronoi cell is on the lower portion of this half plane, but it's already determined by all the other half planes. This is not even affecting the Voronoi cell. You still compute it and intersect it with all the others, but I'm just showing you the ones that don't matter now in dark color, in gray color. Okay, so these don't contribute much to the actual polygon, the convex polygon being the Voronoi cell of this red dot, but they're still there. They're still part of the computation, and you consider all of them, and you end up with this convex polygon. So that's one way of doing it. Now, the question is how fast that is, and it's not very fast. But you can do it for one point, and then you can do it for another point, and then you can do it for a third point, and you build up all these cells, each one being a convex polygon associated with its seed point. And once you do that, you get the entire Voronoi diagram. And then the question is, how long does it take you to intersect these half planes? And there could be n of them for a particular point, because there's n minus 1 other points, and so there's n minus 1 half planes, and for every point you have to consider the intersection of n minus 1 half planes, a linear number of half planes. That's not trivial to do. That's not extremely fast, but you can do it relatively efficiently if you're clever enough, right? So the algorithm here is you have a set of endpoints. You want to put out the Voronoi diagram as the output, and you compute each cell individually, like we just did with this perpendicular bisector business, and there it is animated up here again. And then you want to intersect the n half planes that result from all this perpendicular bisectors. That gives you one Voronoi region. And then you got to repeat that how many times? Linear number of times, n times, because there's n points, and each point needs to, you have to compute the Voronoi cell for each individual point. So the time per cell is, you could do it in quadratic time. Why? Well, you tell me, how can you intersect n half planes in quadratic time pretty straightforwardly based on what we already know and what we've already done? Especially what we've done in the last lecture. It's a hint. The intersection of n half planes. How would you do that? Yeah.
Like we computed the intersection of the convex cells.
Yeah, so a half plane is a convex polygon. How many can see that? It's an unbounded convex polygon, but it's a convex polygon with only one edge. And we already know how to do convex polygon intersection. If you want to intersect convex polygons, we know from the last lecture as you have a subroutine to do that efficiently. By efficiently, we mean linear time. Okay. So you intersect all these half planes. You can intersect them one at a time, and it's linear time with every growing, intersection along the way. So that's n squared if you just do it naively, right? You just call that subroutine n times 1 for every additional half plane. But you don't quite have to do it that naively, right? What you can do is you can intersect the first n over 2 half planes and then the last n over 2 half planes separately, right? And you can do it recursively and do divide and conquer. You can reduce that time to n log n basically for one cell intersection if you work at it hard enough. And then for each cell, you want to do it for one cell per point. For each point, you want to find its cell. And the Voronoi diagram is the union of all the cells, so it's n times that. So the naive algorithm will be n cubed. But then you can find the intersection of n half spaces in n log n time, right? And we already showed how to do that with the slab method, these strips and the trapezoids and all that, and stitching together the results. Bottom line is this algorithm eventually gets down to n squared log n to compute the entire Voronoi diagram of endpoints. Now, there's a much more complicated algorithm than this, and that's out of Ian Shamus's thesis in 1977. The guy who founded all computational geometry with his PhD thesis, quite a monumental achievement. He gives an n log n algorithm for the entire Voronoi diagram, not n squared log n or anything else, just n log n total time. And it's basically a divide and conquer like merge sort. It's like merge Voronoi diagram. You compute the Voronoi diagram of 2 halves, then you merge them together and you stitch along the middle. The stitching part is very tricky. The merge part is very tricky in this divide and conquer algorithm that he proposed in the 70s. So tricky that it takes dozens of pages to describe and analyze, and we won't do it here. The book actually describes it, the Proprietà and Shamus computational geometry book. So for extra credit, if you want to take a deeper dive into that algorithm, be my guest. I'll give you extra credit for it, but we won't describe it here. It'll take too long, and the return on the investment is not high enough to discuss it in class. So that's what this is. So it's a divide and conquer, the very complicated merge step. There's a much simpler algorithm, I should qualify by saying it's simpler than this algorithm I just mentioned by Ian Shamus. That's by Steve Fortune back in the 80s. He showed how to compute in n log n time the Voronoi diagram based on parabolas and a sweeping line algorithm. So the sweeping line algorithm basically does this. It sweeps across the point set from left to right or from any other direction. It's really equivalent. And as it's doing so, it's building the Voronoi diagram using parabolas. And again, it's too complicated to explain here, even though it's simpler than the first one. It still works in n log n time, and usually when you want to compute Voronoi diagrams these days, that's the one you use actually. Also, it has a nice feature. It generalizes to other objects, not just points. It generalizes to disks and perhaps even other objects like segments. And so the Voronoi diagram could be defined for disks, not just for points, right? The locus of points around the disk closer to that disk than to any other disk. And disks could be of 0 diameter, and that's when they degenerate into a point. But now they don't have to be necessarily of 0 diameter being a point, but they can be an actual disk, a circle. So this algorithm, by fortune, generalizes. Separately, we can prove that Voronoi diagrams require n log n time to compute. That's a lower bound on Voronoi diagrams. So that means that both of these algorithms are optimal, right, because of this theorem. So the corollary is both of these are optimal. N log n time is required, and n log n time is sufficient. So both of these are optimal. Now here is Fortune's algorithm running at 1,000 points. So just so you can see kind of how it works, the full effect. This is actually slowed down. I slowed it down by like an order of magnitude. It's n log n, so over 1,000 points, it'll be over in less than a second on a typical computer. But I kind of slowed it down to show you how the wavefront of these parabolas kind of helps ascertain and define the Voronoi cells as it sweeps past them, and that's kind of how it works. Again, for extra credit, tell me more about how this works. Maybe analyze it and look at it. There's a wiki page. It's also in some books. And you can take a look at it. And here is Fortune's algorithm computing the Voronoi diagram of 10,000 points, and now it's running in real time. That's roughly about how long it would take to run on 10,000 points. Actually, it might be even faster than that, but this one I didn't slow down the animation artificially. So 10,000 point Voronoi diagram right there. So it is quick. If this was quadratic, it would take many minutes or even hours, possibly, for that many points. Probably minutes. Any questions about any of those things so far? Okay, and so with Voronoi diagrams, once you construct them, you can solve all these other problems. Euclidean minimum spanning trees. You can solve nearest neighbors. You can solve planar subdivision search in a Voronoi diagram, dynamic cases, and many other things. And there's dozens of other problems that you can solve. You can solve the minimum circumscribing circle problem, like what's the minimum size diameter circle that covers the entire point set. Often you want to compute that. That even has applications. Can you think of applications where you want to compute the minimum size circle that covers a bunch of points, that completely encloses a given point set? There's some interesting applications of that. You can imagine there's probably delivery services kind of problems where you want to find, the smallest circle that encloses all your customers, and that circle is your kind of coverage of your service or delivery options. If you're a trucking company or a delivery company, if you deliver pizzas, you want to find out where you have to put your pizza parlor so that you'll be covering all the potential customers in that city that you care to deliver to, and that's probably where you want to put your service center or pizza place or whatever your operation is, somewhere in the middle, around the center of such a circle. Another application is kind of a military, kind of a darker application. You have a bunch of targets you want to take out with one nuke, say, or one large bomb. And the bomb has a certain destructive diameter or destructive radius. And the question is, what's the minimum size bomb you want to put and where do you want to put it to cover all these targets. Um, your mileage may vary, but that's actually another application of this problem. Anyway, so Voronoi diagrams, very ubiquitous, and now you have, a couple algorithms described and a couple more alluded to, and if you want to read more about it, feel free. Any questions about any of that? Okay. What I want to do next, since we have a midterm coming, I want to tie up a few loose ends on extra credit problems that were pending from many weeks ago. One such problem is the majority problem. You have n elements, let's say numbers, integers. You have n integers, and with duplicates possible. You have, duplication is allowed, and you want to find the majority element, the element that occurs the greatest number of times, more than half. So majority, we mean half or more. So we don't just want the most commonly occurring element. We want the element that occurs at least half the time or more, if it exists. There may not be a majority, and then you just report that there is none. Or there could be two majorities, right? Half the elements could be x, and the other half of the elements could be y, and now both x and y are technically majorities. They're half or more. So you can have zero majority, one majority, two majorities, but obviously not three or four majorities, because half of them have to be one type or another. How many worked on this problem? Oh, good. How many solved it? And by solving, we mean how fast of an algorithm? Because if you're allowed, yeah, how fast are we? N over 2, yeah, so linear time asymptotically in the number of elements or the number of integers. Because if you're allowed n log n time, you can solve it very easily. If you're allowed n log n time, how would you solve it? One word, sort it, and then you'll know, and then you just scan it and see what the majority is. But linear time, it's not so obvious how to do it in linear time. All right, so how do you do it in linear time? Any thoughts or ideas? Yeah.
You would just need to touch half plus one to know if you have majority, right? So then you just go through n divided by 2 linear time elements, and then if you encounter one more, and they're all the same, then you found a majority.
Okay, so algorithmically, what do you mean by touch every one? Let's say you start looking at the elements and they're all different than one another. And how do you even know that they're all different? You take an element, it's different than the second, the third is different than the first two. And how do you even know that without comparing them to all these other ones? And that will take time. So how do you avoid all that expenditure of time? Because that can easily pile up and go super linear, above linear, maybe even quadratic if you're not careful. So what do you say? How are we going to achieve linear time on that one?
You have to specialize constant space.
It doesn't have to be constant space, but you have to watch the space consumption so it doesn't grow beyond linear, say. So you won't be able to use a giant hash table or something like that. I know what you're thinking. Big hash table, right? How big will the hash table have to be? The hash table could be 5 times n or 10 times n. That will do it. But how fast is access to the hash table? Worst case. So he's suggesting an algorithm. I'm kind of inferring from what he's saying. Create a hash table. Put everything in a hash. Yeah, accesses to a hash table are worst case linear, and you can pull some tricks and make them less than linear worst case accesses. How do you do that? Remember the hash table discussions from the second week of class, or whenever it was? Yeah, you can grow height balanced trees off the hash table buckets, and then it won't be quite linear. Worst case, it'll be what? Log. But that's still log. And you have to do n of those. So if you're not careful, it's going to take n log n, worst case. And if you're going to spend n log n time, you might as well just sort and be done with it. That's even simpler. So that's a good try. In practice, it'll work in average case linear. But the worst case is still n log n. So let's try to beat that too. Yeah. Yeah, he's saying group it in groups of 2. Let me give you a hint. Hold that thought for a second, because that's a good idea. Let me give you a hint on a much simpler approach. You use an algorithm that we've seen before as a subroutine. Which algorithm have we seen before that runs in linear time, uses a subroutine that will pretty much solve this problem? If I tell you which algorithm, it'll be obvious. So see if you can figure it out. That's a big hint. We've seen a bunch of algorithms already. Some, a lot of them ran in linear time. Let's use one of them as a subroutine here to just knock off this majority problem pretty easily.
Is it
Median, he says median. How many say, yeah, median is onto something with the median? All right. Anybody want to explain his answer, median? He's right. That's a good idea. Why median? Well, how is the majority related to the median? If it exists. The median is the majority. And if it's not quite the majority, the majority will be right next to it. But really, let's assume there's an odd number of elements for a second. Otherwise, the median is, maybe the sum of the middle two, but, or the average of the middle two. But let's say there's an odd number of elements, like 101 or 1,000,001 or 1,000,000,001. I mean, you can see that the majority, if it exists, is also the median. Yeah. And how fast can we compute the median? Linear time. Remember that complicated algorithm, the double recursion by 5 authors, several of which were Turing Award winners? I mean, that's what it took to find the median in linear time eventually, after decades of trying. Well, once you have that subroutine, compute the median, and then how do you find the majority, if it exists, from the median? Compute the median, and then what? What do you do with the median? Could you just report the median as the majority and walk away? How many say, yeah, you could do that? How many say, no, it's not quite that simple? So what do you have to do extra? Check. One word, check, count. See if that median actually is a majority, because the median always exists. There's always a median. There's not always a majority. So count how many equal to the median, and if more than half are equal to the median, that was the majority. What about the cases two majorities? The median just gets reported one thing. So there can be two majorities if, let's say you have 100 elements, 50 is a majority, the other 50 is also a majority. So, because it's greater than or equal to n over 2, right? In the problem specification, we said greater than or equal to n over 2. So technically, you don't need n over 2 plus 1. N over 2 is sufficient to have a majority. So you can have two majorities. So once you have the median, see if it's a majority. If it's not a majority, and if it is a majority, see if there's another majority. How would you test the case where there's another majority besides the one that is the median that you got reported out of the median subroutine, the linear time median subroutine? How do you get the other median? The other majority, if it exists? Not that hard at this point. Pretty straightforward. Yeah, take one of the other elements, it's not the median, and see if there's n over 2 of those, and if there are, that's a majority also. If not, there is no other majority besides the first one that you already counted out to be a majority. Which element are you going to take out of the other half to test for being a second a majority?
Close to median.
The one closest to the median? You could do that. But there's even a simpler approach. If there's a second majority, which element out of the other half do you have to test? Any of them. How many can see that? If there is a second majority, all of them are that second majority. So take any of them you want. It's even simpler. Or you can do the one next to the median, but might as well take some random one because that's easier. Okay. So that's finding the majority in linear time if it exists. Now let me show you a much simpler algorithm than that, because a median subroutine is a heavy-duty, double recursive, very high constant linear time algorithm. And so it's a misnomer that it's linear time and therefore efficient. It's a huge constant, and it's complicated, it's hard to implement. I'll show you a much simpler algorithm. And to see this algorithm, think about the elements. So let's say you have a majority of green ones and a minority of red ones. I'm just denoting them by X's and O's, color-coded. And by the way, the algorithm we just described, find the median and then check to see if the median is a majority, and then check to see if there's a second majority. It makes a very basic and fundamental and somewhat restrictive assumption. Because if the objects I'm trying to find the majority of are not well ordered, like if they're pointers or if they're graphics objects or if they're complex numbers or if these objects are matrices, how do you sort a bunch of complex numbers? How do you sort a bunch of matrices? How do you sort a bunch of animals or vegetables or minerals? Majority is still defined for all these classes other than numbers. How many can see that? It's just how many of that type equal to each other? There are. And if there's more than half, then that's a majority. Republicans and Democrats could have a majority of one or the other, or independents or anything else. But these sets are not well ordered, so you can't sort these sets in a natural way. There may not be a total ordering defined even on the set, much less something that you can easily compute. This algorithm I'm about to show you now is not only simpler, but will work just based on equality or inequality, not based on total ordering. So sorting may not even be defined here, but there's still a majority here, and it will be found. And it'll happen in linear time, and it's pretty simple. So that's a total order. So that solves the second problem that I posted way back in the slides. Do the majority in linear time, but this time, don't rely on total order. Just use equality or inequality, not greater than or less than relationships. So sorting isn't even defined, and median, therefore, isn't defined either. So you can't use the median subroutine anymore in this scenario, because things are not just greater than or less than. That's undefined. They're equal to or not equal to. That's still defined. So median is useless now. All right. Let me ask you the following question. Let's say there was a majority here in this set. And I take a pair of elements that are unequal. One of them is an X, one of them is an O. And I remove them from the set. I throw them out. What can you tell me about the remaining elements in the set with respect to majority? If I take out an unequal pair, what is true still about the majority in the original set? Unchanged. How many can see that? Yeah, if there was a majority before, now take out two different elements out, that majority that was there before is still the majority there now. If it existed to begin with. If a majority didn't exist to begin with, and I took out an unequal pair, that may screw things up a little bit. Whatever remains all of a sudden can become a majority. But if there was a majority before, it remains invariant, unchanged, by taking out an unequal pair. So it's not an if and only if, it's just if I take out an unequal pair, the majority did not change. If it existed to begin with. If. Okay. Well, that suggests an algorithm right there. What's the algorithm now? So this is an insight. It's not a trivial insight. Happens to be true, but it's called an invariant. In general, an invariant is something that doesn't change. That's why it doesn't vary. It's an invariant. It doesn't vary. It's a property that when you hit something with some operation, the property is preserved. It doesn't change. All right, so removing an unequal pair preserves the majority if there was a majority there to begin with. So what's the algorithm now? We're not done. This is just an interesting insight, but I'm telling you that based on that, you can solve the rest relatively straightforwardly. Yeah. Another object? Oh, you want another object in there? Okay. That's always good to make it a little more general. One, two, three, four, five, six, 7, 8, 9. And let's keep the circle a majority. But now there's a couple of triangles too. Yeah, so the green circle is the majority. So what you want is to remove unequal pairs. If you can find a pair that's unequal and throw it out, the majority element didn't change if it was there a majority to begin with. So that's an invariant. Now the question is, how do you remove an unequal pair? How do you find an unequal pair so that you can remove it? Once you find it, it's easy to remove. Let's say they're all sitting in some big array or whatever, some data structure. So if you just take the first two elements in the array and they're these, you can just remove them and the problem doesn't change. And if you take these two elements and remove them, the problem doesn't change. And if you take these two elements and remove them, the problem doesn't change. But there's an issue here, right? How you guarantee to find two elements that are different? What if you take two elements, like the first two elements of the array, and they happen to be the same? You can't throw them out. And if you put them back into the array, you haven't reduced the size of the problem, and you just wasted some time, and the problem size did not decrease. But there's something you can do. So if you can find in constant time a pair that's unequal, you can remove it, and the problem size decreases by 2. So you spent maybe constant time, hopefully constant time, to find an unequal pair, remove it, and the problem size diminished by 2, which means if you keep spending constant time for every pair that's unequal and remove them, eventually the problem in linear time will vanish to a very small size, and then you'll have your answer. But how do you do that in constant time per pair and avoid cases where you take out a pair and they're the same? They're both green circles. What do you do then?
If they are the same, just pick one of them and
You say pick one of them and throw the other in. You have to be a little careful. Here's what you can do. You can say, okay, if I take these two guys and they're both green, and I look at them and they're both green, I can combine them into a single piece of paper And now this single piece of paper will have a multiplier of 2x. So I'm saying this piece of paper now will have a multiplier of 2 on that. So you it's basically what you're saying is to throw one back in, but you're throwing both of them back in, but combined into a single object. Okay, and next time you pick an element, let's say these two, and they're unequal, you can throw them out. But if you pick two elements that are equal, you can put them in with a multiplier. Now let's say the two elements that you pick are this one with a multiplier of 2, and then this one of these black triangles. What if you pick this pair now? So each guy now in the set will have a multiplier, and this has a multiplier of 2. If you pick this dark triangle and this double green circle, what do? One of them will cancel out the triangle and be thrown out, and the other one, without the multiplier of 2, just multiplier of 1, will be put back in. How many can see that? So you've done a virtual cancellation. Yeah. And what if you take one with a multiplier of 7 and one with a multiplier of 5? And they're both different. Just the two multipliers are 7 and 5. The 5 will cancel against the 7, yielding 2, and the 2 goes back. And you've canceled 5 simultaneously. And if you pick two that are the same, you took 2 pieces of paper and returned 1 piece of paper with a multiplier of 2, and you're still reducing the problem size by at least 1 piece of paper with every iteration. And now you have a general rule of what to do when you pick any arbitrary pair of objects with their respective multipliers. Some cancellation will happen, or merging will happen every single time. How many can see that? You're not wasting work. You're always making progress now by following this simple rule. Yeah.
So when you cancel from like 7 and 5, then you get 2. But what if there was another that was 4, 7, 5, and 4? Now that 4 one will become the majority instead of the 7.
So far, we're just doing this blindly, and there could be other multipliers. So I'm not saying that all the green ones will be multiplied right there on that set. There could be another 3 green circles over here separate than these 2 green circles. That's okay. If you happen to pick up a multiplier of two green circles and 3 green circles, you combine them into a single set of 5 green circles and put that one back. That's okay. You do that.
No, different ones. I mean 7 circles and let's say 5 of triangles.
7 circles and 5 triangles. 5 will cancel the 5. 5 circles will cancel the 5 triangles. Those will go poof. And back in, you will put in the 2 circles as an element.
But what if there were 4 triangles also? And you just looked at the starting.
You're asking what if there were 4 triangles? Where are the 4 triangles?
Basically you have
Se-
like three multipliers.
Yes,
So 7 are circles, 5 are axes,
yes.
and 4 are triangles.
Oh, we just pick up arbitrarily one pair of objects. We do the either merging or cancellation. We put it back. We only worry about the other ones in future iterations. So there could be many sets of multiplied triangles. There could be 5 triangles here, 3 triangles there, 2 triangles there. We don't worry about all of them in one fell swoop. We take 2 pieces of paper, 2 come out, and 1 goes back in at most. That's one operation. Doesn't matter what else is true about the set. Those will be taken care of in future subsequent iterations. Those will get canceled too eventually. So what we're doing is taking 2 pieces out, either merge them if they're the same object, or cancel them against each other if they're separate objects, and whatever left over after the cancellation, if any, that goes back in as a single piece of paper with a multiplier on it. So 2 pieces of paper come out, 1 goes in. It's like the inverse of Thunderdome. 2 people come in and 1 comes out. How many even know what I'm talking about? Okay. Mad Max fan. Okay. So at every iteration, 2 pieces of paper are leaving and 1 goes back in. Guaranteed. At most 1, because both of them may disappear. But at least 1 less piece of paper is there with every iteration. Now, which 2 pieces of paper are you going to pick at every iteration for this to work? Which 2 pieces of paper? Do you need to specifically find 2 different ones? No, because if they're the same, you merge them. Add the multipliers, put that back in. Do they have to be something with a multiplier of more than 1? No, any multiplier will do. So which 2 pieces of paper do you take out at every iteration? Any. Take the first 2. So now you can really implement it as an array. You have an array of these objects. Take the first 2. They either merge or they cancel, and at most 1 goes back in, and now the array is 1 less. Then take the first remaining 2 in the array, and keep going. How many see this algorithm now? Okay. A couple of loose ends. Let's say you take everything out, and at the end, there's 1 lone object left. Let's say we took these 2, and they canceled. Then we took these 2, and they canceled. And then we took these 2, and they canceled. And now that's the only one left. What do you do now? Is this the majority automatically? I mean, say, yeah, that's a majority guaranteed. I mean, say, not so fast. Why not? Yeah. You got to check it. Because this process will work and cancel everything against everything else, whether there's a majority or not. See, all the elements are unique. They're all unique, unequal integers. Or objects, not necessarily integers. This cancellation will happen over and over and over, and there will be 1 left. But it's not the majority. Not only that, there is no majority. Not only that's not the majority doesn't even exist. So when you have 1 left at the end, you better check it. How do you check it? How fast? What does it mean to check it? Count out how many times that object actually appears in the original list. That's linear time, obviously. And then you'll know if it's a majority or just whatever's left over that's not necessarily a majority. Because remember, we said that once you eliminate a pair that's unequal, the majority that's in the set, if there was a majority to begin with, doesn't change. Let me put it more simply. The majority doesn't change if you eliminate an unequal pair if there was a majority there to begin with. But that's an if. That's a conditional. If there was no majority there, the majority doesn't change either. Because there was no majority there before, and there's no majority there after. But doesn't mean what's left over at the end of this process will be a majority. It doesn't have to be a majority. It could be a non-majority, because the majority may not exist. Question?
What if we remove one green and we have only 6 of pairs? If we are removing the unequal pair, then there is nothing left.
Yeah, so if you remove unequal pairs and you have left something that's a non-majority, you're saying? Okay, so let's sort of do what you're suggesting. So 4 green, okay. Very, very good point. I should give you extra credit just for asking that. All right, let me paraphrase what she's saying. She's saying, what if you remove unequal pairs? So let's remove this pair first, okay? Then we remove this pair, okay? Then we remove this pair. And finally, we remove this pair. And there's nothing left, right? Very good. We know what extra credit. Submit that to the class website. That's a very good insight. That's a boundary condition. How many, first of all, see that can happen? The majority could be eliminated by successive cancellations against other things that are not equal. Okay, so what do you do? Wait, let's not be so hasty. There is a majority there. Remember, majority is n over 2 or more. So out of 8 elements, If 4 were the same, that's a majority by definition. So there is a majority. It just got canceled out in this process, and now there's nothing left. So what do?
We can stop at if we are left with one or two.
Ah, so don't wait till the very end when it's empty, but instead do what? Yes. Leave the last 2 elements. When there's 2 left, don't cancel them. Instead, check those for being the majority. And if there was a majority, the last pair standing will contain that majority. Because that majority was enough to cancel every other thing, and it will persist till the very end by this invariant. Right? So that last pair, leave alone, check both of them for being a majority, and either one of them will be the majority, in this case the green guy, or both of them will be the majority. If there's 2 majorities, they'll both persist to the very end. The last pair standing will contain both majorities. How many can see that? Yeah. So excellent point, easy to fix. What else? Anything else? Is there any other loose ends? So when you implement something like this, yeah, go ahead. Yeah, so another excellent point. So he's saying there's 2 last pieces of paper ending up in the set. Don't necessarily have to have a multiplier of 1. They can have a multiplier of greater than 1. You can have one piece of paper labeled with 7 circles and another piece of paper at the very end labeled with 7 triangles. And now you're trying to cancel 7 against 7. But so we have to kind of generalize that solution to not just the last 2 elements, but the last 2 pieces of paper with multiple elements on each, with a multiplier. But either way, it's the very last pair of multiplier elements with multipliers. So if you have 7 left and something else, one of those 2 will be the majority, or both will be the majority, if the majority exists. Or neither may be the majority. But that's the only 2 things you have to check. Yeah. Yeah. There may not be a majority. Yeah. That's why you have to check. You have to check both. So maybe 0 majority, 1 majority, or 2 majority. Okay, so when you implement something like this, now, do you really have to take it out of the array, look at them, do the cancellations, put it back into the array, and do it like that literally? No, you don't. What can you do? Take the next one. So basically, have all these guys there, and have an extra variable that holds, one of them. And you take the next guy in the array. If it's the same, you eliminate it. If it's equal, you have a multiplier now in your hand. If it's the same now again, the multiplier clicks up. If it's not the same, the multiplier clicks down. So all you need is this variable, that's my hand. And you take every element now into my hand and either clicks up the multiplier if it's the same as the element that I have in my hand. If it's different, I click down the multiplier and it gets eliminated. You see what's going on? So I don't even have to take 2 out and put 1 in. I just take 1 out at a time, have this constant variable in my hand that's the latest element. And if something gets eliminated with a higher multiplier, the type of object in my hand gets to be that other object with the difference in the 2 multipliers now instead. How many can see that? So when you implement, it's even simpler than having an array and putting papers ins and out. Paper is it's not even papers, it's elements coming out. The multiplier is really just in my hand. as an extra integer multiplier of the object that's in my hand that's the type of the ones that I'm keeping track of. So in that scenario, when does this end? How does this end? When I have how many elements left? Essentially one in my hand and one in the bag, or one in the array. Or maybe none in my hand and two in the array. Either one, that last two elements that you have either in your hand or in a bag or just in a bag or just in your hand, just check those for majority. So the implementation is even simpler than that. How many lines of code are we talking about now to implement this with this one extra variable and one extra multiplier? And the array is just the input array, which I don't even have to modify at this point. The input array is just constant, it's fixed. I just step down the array and do the cancellation in that variable I have in my hand, and the other hand I have a multiplier. How many lines of code are we talking about, roughly? 10, 8, 7, 12, it depends on the language, but very few lines of code. One loop, and an if statement and a couple of assignments, and that's the end of it. How simple is that? And it doesn't rely on sorting. And it sure as heck doesn't rely on median finding with double recursion and all this giant overhead constant, and look how simpler it got. Because with the median finding algorithm, if you have to unroll that into a large piece of code, I mean, that's hundreds of lines of code to find the median, plus a huge constant. So you see how, you keep refining the algorithm more and more, and as you refine it, it gets simpler and simpler, and also more efficient, hopefully, and also less lines of code, and also more foolproof, because if you have just 5 lines of code, there's not a lot of places where errors can hide. Truth is just staring at you in the face. It's beautiful, it's elegant. Right? Bugs have no place to hide in just a few lines of code. But if you have hundreds of lines of code, there's a lot of bugs in there, most likely. So that's another beautiful algorithmic design. My gift to you. Any last questions? All right. See you next time.